So first of all, many thanks for the organization of this very nice conference. Specific thanks to Erika and Cheng. So I hadn't been here for several years, actually, so I see the changes now in the scene. So the topic of my talk will be pretty much connected with some of the talks that we have already heard this morning, in particular because this is connected also to phi-4 models. But actually, what I'm going to talk about here, so it's about Gibbs measures, so invariant measures also, but it's for a model which arises in Bose-Einstein condensation. So this is so there are connections with phi-4 model, but there are also differences, and this is what I want to insist on here. So this is a joint work with Arnaud Debussche, who is not here anymore, and Reika Fukuizumi, who is a Japanese collaborator from Waseda University in Japan, with whom I've been studying, analyzing some SPD models in Bose-Einstein condensation for quite a long time. But up to now, we were mainly dealing with regular SPDs, and in this case here, the equation which we consider presents some singularities, and then I will mainly talk about the two-dimensional case, which is the first case which starts to be singular. Okay, sorry. So this is the outline of my talk. So I will first introduce the model. So first of all, I apologize. Maybe some of you have already heard the talk before, so sorry for that. So I will first introduce the model and explain where it comes from. This is actually a mean field model in Bose-Einstein condensation. And, well, at least the deterministic model is rigorously a mean field model. And I will talk a little bit about how we treat the evolution SPD, so the dynamics, and why there is some singularities here. This is quite, I mean, you've heard already arguments about these kind of things. Then I will talk about formal Gibbs measure, and how we interpret, prove the existence of the measure in the regular case, which is a one-dimensional case. And then I will explain the first construction we had with Arnaud and Rika a few years ago, 2 years ago. But this construction, which was just quite abstract, did not give us any information about the Gibbs measure. So I will also mention some more recent work about a second construction, which uses the Bouard formula and which allows us to give much more information about this measure. Okay, so what about the model? So I said it's about Bose-Einstein condensation, so probably you've heard about it. It consists in cooling some atoms, some boson gas, typically dilute boson gas, in a very, very low temperature, very close to the absolute zero. So the context is like this. You have N particles, capital N particles, quantum particles in a trapping potential. So V is a trapping potential. And so the wave function of these quantum particles satisfy linear Schrödinger equation. So the wave function depends on T and the coordinate x1, xn. And it satisfies this Schrödinger equation with an Hamiltonian h hat, which is given by this. So because these are quantum particles, you have this Laplace term that acts on each j. V is, as I said, the confining potential. And we take into account two-body interactions. That is, we have an interaction potential, un, of xj minus xk. Okay? And as I said, the model we'll be considering is a mean field model. So we are interested in one marginal, that is, we fixed a particle xj and we send n to infinity with a specific scaling. And we wonder whether we can have an equation for the wave function for one particle. Okay. So of course we have to make some assumptions. So the first one is that we have a boson gas, which means that the wave function is symmetric with respect to exchange of particles. And also, so this has to be proved, actually, but what will happen is that, so this is only a formal derivation, okay? I will not prove anything here. This was an old work, actually, that was done by other people before. So you can expect that when n is large and you fix one particle, then the wave function, the particles will behave like if they were independent and identically distributed, and that the wave function will be given by this kind of expression. Okay, and then you have to make some assumption about the interaction potential, sorry. And so typically, if UN, so in the Millfield regime, UN will be of the form 1 over n u of x. And for example, the most classical potential you can take for u is the Coulomb potential. And then if with the previous assumption, what you can see is that by the law of large number, if you think of your particles as being independent and identically distributed, and if you fix the particle j, as n goes to infinity, this term will converge to the expectation of u of xj minus x1, expectation in x1. And so it can be expressed with the wave function like this. And what you get with for your wave function psi, which was written here, sorry, here, what you get is what is called the Hartree equation, which is a nonlinear Schrödinger equation, but instead of having this cubic term here, what you have is a convolution of a modulus of psi square with u, okay, times psi. This is called the Hartree equation. Now, if you have a dilute gas, which is the case for Bose-Einstein condensate, then you are in a different scaling, and you typically what you take is un of the form n square u of nx. And you can see this as, actually, you can see this as 1 over n cube u of nx, right? And this will typically converge to a delta function. Okay, the 1 over n is for the Millfield limit, and so what you get at the end is this cubic nonlinear Schrödinger equation with, in addition, this confining potential here, which will play a role in what I'm going to explain. Okay, this was proven some time ago by the people. Well, this is called the Gross-Pitaevskii equation, which was first derived for superfluids in 1961 by Gross-Pitaevskii, but the rigorous proof of what I'm mentioning here was done by, for the Gross-Pitaevskii equation, really was done by Erdos, Schr, and New. Okay. So, okay, but now we're interested in a case where the atoms are not, I mean, the temperature is not so close to the zero, but just a little bit above. It's close just a little bit under the critical temperature of condensation, which means that there are the macroscopic part of the atoms which are in the condensate, which are condensed. But there are still atoms which are excited. And then you have to model the interactions between the condensed atom and the non-condensed one, the excited one. And typically, so there are many ways that physicists use to model this kind of things, but one of them is to consider that the non-condensed atoms are thermalized, and they consider this part, which is the, orange part here, which is called the incoherent region, as a thermal bath. So they used the previous model, but they had, and I write the equation here, so it looks a little bit complicated, but I will write it in a more mathematical way by erasing all the physical constants after. So you have, so if you assume first that these two terms are, so if you remove these two terms and remove this PC, you get exactly the previous Gross-Pitaevskii equation. And we have additional terms. So LGP is the operator that gives you the Gross-Pitaevskii equation I've mentioned before. Okay, and and these two additional terms just gives you the dissipation, diffusion, and the noise here. So these two terms represent the interaction with this thermal bath. And okay, it's pretty much done in a way that you know that there will be a thermalized state, okay, for the equation. So here, this W is a space-time-white noise with an intensity gamma, which is connected to this term here, and mu is what is called a chemical potential, okay? And there is a last thing, there is this PC here, which is a projection on the coherent region that we will not take into account afterwards, but that usually physicists take into account because they see very well that this equation diverges if they don't put a projection on the equation, okay? And so the model that we are going to, so it's the same as the previous one, except that I have erased all the physical constant except for the chemical potential, but I will also take it to be equal to 0 for simplicity. Is written like this, okay? So I recall that psi, my psi is a wave function, so it's complex valued, okay? I had this confining potential V that I take equal to just the multiplication by x², okay? This is the most common thing that you can do. And so it means that this operator A is the harmonic oscillator minus Laplacian plus x², okay? And I have this nonlinear term. I have the dissipation, the dissipative term, which is minus gamma A psi. This noise term, so I recall that dW by dt is a space-time-white noise. And this nonlinear term, and there is a I here. So gamma, in principle, is a small constant, okay? It's positive, of course, but it's small. Should be small. And there is this I here, which comes from the original Gross-Pitaevskii equation. Okay? Yeah? You have a question? No? Okay, so as usual, we decompose the W, so it's a complex space-time-white noise. Okay? And so we decompose it as usual on a complete orthonormal system. So here, because it's complex, we have a sequence of independent complex valued Brownian motions. And we decompose it on a complete orthonormal system of L2 over D, real valued because I put the complex valued in the beta k, but we take the complete orthonormal system, which is made of eigen functions of the operator A. So typically in dimension 1, these are Hermite functions, and in higher dimension, these are products of Hermite functions typically. Okay, and the eigenvalues grows like this. So like twice the, well, it's linear in the length of n, okay, when you have a multi-index. So it goes less rapidly than the eigenvalues on the torus, okay, but this is not the main point. Okay, and I recall that, as we already seen in previous talks, we have an energy here, so which would be conserved for the purely Hamiltonian system, that is, if gamma was equal to 0, it would be conserved for the equation, okay? And, and it will also play a role, of course, in order to define the Gibbs measure. So what about the evolution equation? So this is very classical. We have stochastic partial differential with an additive space-time noise. So we first solve the linear equation. So we've seen already this several times. So here, the linear equation, which is called Z, is again complex valued, but but it's still Gaussian. It's a Gaussian complex valued Gaussian random field with a covariance given by the operator A minus 1. Okay, well, you have to adapt because this is complex valued, but okay. And it's also, of course, the stationary solution, my Z of, well, I take it like this. I mean, I don't take the initial state at 0, but I consider Z as being the stationary solution of the linear equation, which is given by this stochastic convolution. Okay. So you can decompose it as you want. And what we hope is, of course, that if we write the solution psi as V plus Z, then V will be more regular than Z, as we've seen already, for example, for 5-4 models. So V will solve this equation, and so the problem that arises is that Z may not be regular. And actually, so we choose to measure the regularity in Sobolev space which are built on the operator A, because that is rather natural in this context, because for, as Annie said, for the Schrödinger equation, it's better to use this kind of Sobolev spaces, but here we cannot really work about Sobolev spaces based on L2, and this is due to the regularity of Z actually, and this is really due to the specific confining potential that we have. So actually in dimension 1, everything is okay, because so it's like the 5-4 model. In dimension 1, Z is has values, so it's not exactly, because Z is not L2 valued, but is homoscial in LP, and actually it has bounding moments, of course, in LP, for any P larger than 2, okay? And so it has a little, of course, you can measure the exact regularity because everything is more or less explicit. This is Gaussian, you can do everything. But it's okay because it's, at least this is a function, more surely. So you can take the powers of Z to compute the equation for V, which I recall is written here, okay? Now, when D equals 2, so in this Sobolev space, which are recalled are based on A, which means that S measures the regularity, but not only the regularity if S is positive, you have S regularity in LP, S derivative in LP if you want, but you also have some decay, which is, sorry, you also have some decay, yeah, typically, which is that x to the power S is also in LP, in this Sobolev space. Okay? So in dimension 2, what happens is that Z is only in WSQ, but for Q larger than 2 and SQ larger than 2. So typically, if you send Q to infinity, the larger Q is the smaller you can take S, okay? But still, if you send Q to infinity, you will be 0 minus of regularity. So it's never a function, okay? But you have to send Q to infinity to get 0 minus. And it's not like 5, 4, 2, for which you have H2, H1, sorry. You have L2, just positive and negative amount of regularity in L2, right? And here, on the torus, I mean. 5, 4, 2 on the torus. So here you have to play also with the. So in this case, we need a renormalization in order to be able to beat the powers of Z. And we are not on the torus, so it's not the completely classical renormalization that we have, but still it's the same thing. That is, you consider the white noise, which is given by A to the power 1/2 Z, which can be written like this. And you consider the Gaussian space generated by Xi. You decompose it in Wiener chaos. And so if you first cut, so you project, the capital N here stands for a Galerkin projection on the first eigen functions of A, so the first Hn. So this is perfectly well defined, and this is perfectly regular, so there is no problem in defining Zn to the power k. And so the weak product will be just a projection of this power on the kth Wiener chaos. So just I do not insist on this. I'll just give some example because the fact that it's complex value changes a little bit the value of the constants, because you have to think that Z, the real part, and so the if you consider this psi a to the power 1/2 Z, then the real part and imaginary part are two independent white noises. Okay, space white noises. Okay, for fixed t. So this is the formulas that you have for the renormalization, for example, for these two terms, where, as usual, so this rho and square, which may be expressed like this, is exactly the variance of Zn, but now it depends on x. It has no reason to be, it's not a constant in general, it depends on x. But it diverges as n goes to infinity, of course, because of the regularity we have on this term. But anyway, we could prove that the weak products that we need converge in any LQ of omega with values in W minus SQ, where S and Q have the same conditions as the regularity of Z. That is, we need that SQ is larger than 2. So it's the weak product converge in the same space and have the same regularity as Z. It's because since we only lose an epsilon of regularity, we still are able to prove the convergence in any space like this. Okay. Okay, and there is a connection between the kernel. So this is the kernel of the projection of the operator A minus 1, and you can express exactly using the weak product on the left of this Nelson formula. You can express these moments in W minus SQ in terms of some norm of this kernel Kn, and this will play a role also afterwards. Okay. And once you've done that, then it's not very difficult to solve the problem by rewriting the equation for V, and we can prove that there is a local solution in this space that V, if the initial data is more regular, actually V is more regular, it's in LQ, and we can get an LQ bound as was done by Moura and Weber for 542, and get, for gamma small, we get this LQ bound, and then we get global solution, sorry. For gamma larger, for gamma large, you can get this LQ bound and a global solution. For gamma small, you have to work a little bit because you don't have this LQ bound. But anyway, you can solve the problem. Okay, so let me now turn to the Gibbs measure. So we've heard already about that. So there is a strong connection with quantum field theory, as I said, with the 5-4 models. And actually, in this case, so the mean field problem on the Gibbs measure was an old problem also that was studied in I think, 60s. Well, there are some rigorous results by Mathieu Levin and others, and some more recent results, actually, on the mean field limit for the Gibbs measure for the n-particle system. Okay, but I'm not talking about that here. And okay, so there is a strong connection with these topics, but there is also, on the other hand, people who were interested in proving and using the existence of invariant measure for the purely Hamiltonian system. You see here what we have. We have infinite dimensional dynamical system which has a mixed dynamics, so we have an Hamiltonian part, and we have a dissipative part with a space-timewhite noise. Okay, so it's exactly as in Navier-Stokes equation, and earlier you have a kind of, well, exactly, not exactly, because it's really Hamiltonian here, but it's connected with that. Okay, we have a mixed dynamics. And so people were interested also in studying just the purely deterministic dynamics, but that you can, you can also look at invariant measure for that. And actually, you have the same invariant measure for the purely dissipative dynamics, that is when you remove this Hamiltonian dynamics, or where you remove the all terms depending on gamma, or when you mix all the terms, okay? And this is really easy to see by looking at the generator of the transition semigroup associated with this system, because formally, so if you formally write the Gibbs measure like this, so I recall that we had this energy H, which I had written before, which was the energy which is conserved for the Hamiltonian dynamic, the Gross-Pitaevskii equation. So if you write formally this Gibbs measure like this, so this generator of my system has a first order term which comes from the drift here. So this first order term has got a part which has this J gradient hash part, and the dissipative part, which is this minus gamma gradient hash, and it has a second order term which comes from the noise, okay? So when I test this formal measure against the generatable by 20 function phi, acting on my infinite dimensional space, well, formally, all the terms depending on gamma will cancel by integrating by part. This is only formal, of course. You would have to project on finite dimensional space if you want to justify this, but okay, this will cancel by integrating by part this term, which will give you this infinite dimensional Laplace operator. And the last term will also be equal to 0, because this term here, J grad, is like an infinite dimensional rotational, because J is a multiplication by A, but okay? And it's orthogonal to gradients, okay? So this term is also equal to 0, which tells you that actually this Gibbs measure is formally invariant for the Hamiltonian system, okay? So formally, this Gibbs measure should be invariant for our system, okay? And we've heard already how to deal with that in the regular case. So we don't have, in infinite dimension, we don't have a Lebesgue measure, but we can consider just the quadratic part of the energy, the term which is written in red here, okay? Which gives us the Gaussian measure, which with a covariance operator A-1, okay? And so in dimension 1, everything is easy. Actually, this was already studied a long time ago by Burtoman and Zeka when they studied the Gibbs measure for the Gross-Pitaevskii equation. Because as we saw before, this Gaussian measure with covariance A-1 has support in LP for any P larger than 2. So in particular, this term here is well defined and regular with respect to this measure. So you can perfectly define the Gibbs measure in dimension 1. Okay, and they proved that actually the Gross-Pitaevskii flow was well defined on the LP space. Well, that was known already, and so there is no problem in proving that this is, and we can do the same also. We can define the flow and prove that this is an invariant measure, no problem. Okay. Now in dimension 2, the problem starts because, so as I said, the measure mu, so the law of Z, has only support in W minus SQ. So what happens for phi 4, 2 on the torus is that you can still define the term in the formal density that you have with respect to the Gaussian measure in the previous slide. So sorry, excuse me. Yeah. So you would have, of course, in dimension 2, you would have to replace this term by the weak product. Okay. And then for 542, what happens is that you can define this integral of, this is the integral of, it would be the integral of psi 4 dx. Okay, so 542, you can interpret this as the duality product between the weak product and the function 1, okay, on the torus. Here you cannot, because the function 1 is not in any positive WSP space, because it has no decay on the space, okay? So it's a priori not well defined. So what we did 2 years ago is just considering Galerkin approximation of the purely dissipative equation, because the invariant measure is the same for the purely dissipative or the mixed dynamics, okay? And we proved that, so we project it on a finite dimensional space, and by decomposing more or less we consider stationary solutions of this equation, finite dimensional, so we had to use a smooth cutoff. This is a detail. And so we considered stationary solution, and we decomposed the system as we did before for the evolution equation, and we could prove some bounds which showed that this family of invariant Gibbs measure, finite dimensional, was tight, and so we had a limit, okay, for up to a subsequence. But then that was all. I mean, we are not able to prove any uniqueness of the limit or any properties of this weak limit, okay. And so then with Reika, we started to look at what was done for the 543 equation, and that led us to consider a second construction. So typically this Gibbs measure, as I said, should be given by like this. So it should be the integral of minus this integral of psi 4 dx against the mu being this Gaussian measure, so with covariance operator A minus 1, okay? So the first thing is to make sense of the partition function, that is the integral of this term, okay? And I mean, its limit, you take the cutoff here, that is you put a pi n psi in this term here. So this is what I call Rn of psi, okay? And I want to make sense of this term with, I want to take some limit of this term with, I put a Rn here, okay? So now suppose that this Rn converges to some R in L2 of mu, then if in addition I have a bound, a uniform bound on the exponential minus Rn, then the density will converge in L1, and my limit measure will be absolutely continuous with respect to mu, okay? Now, what happens here is that if this were true, then of course the L2 of mu norm of Rn should be finite. But if you, it should be bounded in N. But if I look at this supremum here, actually you can compute, you can compute exactly the Rn norm L2 of mu, squared norm of Rn in terms, as I said previously, in terms of the kernel Kn of pi Na minus 1. So if this was uniformly bounded, then it means that the kernel K of the operator A minus 1 should have a finite L4 norm in both variable x, y. And actually there's a miracle that there is an explicit, there is an explicit, more or less explicit, not really explicit. This kernel is not explicit, but the REL kernel is explicit, so we can do some computation and show that this is infinite, actually. And that was actually thanks to Didier Robert, who explained us how to do that. Okay? So this is infinite. So we know that this constant goes to infinity as n goes to infinity. Okay? And so, as I told, we started to look at what was done in 543 or for other equations. So the mention here the work by Barashkov and Gubileni, where they show first they show a variational formulation and then the singularity of the Gibbs measure for 543 on the torus. And it was, the method was used by Bjorn Brinkman and then also by O and his collaborators to study the construction and study the singularity or regularity for the damped wave equation with R3 nonlinearity on T3. And as I said, the main issue is to make sense of the integral of a limit in n of more generally the expectation of this, but take in particular the limit in n of the expectation of minus Rn of z, okay? Which is the integral of this. So it would be the limit in n of the integral of S, where I put a pi n here. Okay. And what they used was the Bouard and Dupuy formula, and which allows, which helps a lot, and which I write here. So I consider finite dimensional projection here, okay? So, so I write it, the formula in more or less in the context that was given by a paper by Stenel. So if we want to compute this partition function, so we can do it by considering the infimum for all drifts which are which have, so the theta have this regularity, so h1 0 in, by just remembering that z has the same law as a to the minus 1/2 w of 1, where w is a Wiener cylindrical Wiener process. Okay. So the infimum of the expectation of, say, Rn of z plus this term here, or plus, sorry, 1/2 of the integral of theta dot square in H. Okay, so yes, that's a remark which I think I don't have really time to talk about that. Okay. And so how do we use that formula? So which helps a lot to linearize in some sense this exponential term. So we want to compute the minus log of gamma n, so my partition function, as the infimum. So we want to show a bound from below in these terms, okay, to get a bound from above on this gamma n as n goes to infinity. So the first guess would be to take a drift that would be uniformly bounded in a minus 1/2 h1 in n, okay? But if you do this, actually you are in trouble. Why? Because if you decompose Rn of z plus theta of 1, so I recall that Rn is given by this, this term here, in which I forgot sorry, so I forgot, Rn I think was with the integral, but okay, it's not a problem. Okay, so you decompose it like this, so the first term, the expectation will be 0 because this is in a fourth order chaos. All these terms may be bounded from above and also from below, I mean, by the fact that your drift would be bounded in this space, and because all the weak products are bounded in W minus SQ. And all these terms are at least quadratic in theta. That makes things work, because my drift is only bounded in so A minus 1/2 H1, which means that I only have the W12 norm of theta of 1 at n, okay? But the trouble is the red term here, so the weak power of order 3, because this term is linear in theta. Okay, so I cannot handle it because my weak product is only bounded in W minus SQ for SQ larger than 2. So if I wanted to take Q equal 2, I would have to take S larger than 1. Okay, so I cannot handle the product here. Okay, so there is a problem with this term, and actually, so the idea, which was already used by other people, but the idea is not to use uniformly bounded drift, but to decompose it as a uniformly bounded part psi n and a term yn, which will diverge as n goes to infinity, and which contains which will cancel the problematic term, the red previous problematic term, okay? And this is done in computing, when you put theta equal this is done in computing this term here, where you will have exactly this third order weak product with the theta n term that appears. But to the expense of subtracting a constant Cn, which is given by 1/2 of this term, which again goes to infinity, okay? Okay, so I think that because my time is almost over, I cannot give more details about that, but this allows to prove everything, that is to prove that Rns is uniformly bounded, that so the family of measure is tight in W minus SQ, so in the same space, that the limit is unique, that any convergent subsequence, of course, converges to this measure, but also any convergent subsequence of the previous constructed family of, I mean, it means that the measure we constructed previously is also equal to this limit. And we have the invariance for the flow, but only for gamma positive, okay? And as far as I know, for gamma equals 0, this is still an open problem. And this allows to show also that rho and mu are singular, mutually singular, and we can construct exactly a set which has mu measure 1 and rho measure 0 by choosing well a sequence, a subsequence nk of n. So, and considering the set of functions in W minus SQ such that the limit of Cnk to the power minus 3/4 times Rn of u is equal to 0, where Cn is the same constant as talked previously, okay? So I think I have to stop. I'm sorry, I'm late, so I won't give the arguments of. I have more time?
Including questions on
sorry, I thought I had 3/4. Okay, so, okay, that's good. Okay, so I can give the arguments of proof. Okay. Yeah, I have one. Yeah, okay, I have still 10 minutes. That will be, yeah, a lot. Okay. Okay, so I recall that Cn was the L2 of mu squared norm of Rn, okay? And this goes to infinity. So the Rn, the L2 of n norm of Rn is Cn to the power 1/2, okay? Okay, so that we have that the L2 norm of the Cn minus 3/4 Rn is of course equal to 0, and so there is a subsequence that that converges to 0 almost surely, and that shows you that for this subsequence, okay, if I define the set S as I did in the previous slide, like this, okay, for this specific sequence, then I get mu of S equal 1, okay? Because for this sequence, okay, it converges mu almost surely to 0. So the mu measure of the set where it converges to 0 is equal to 1, okay? Now I have to prove that re-extracting possibly a subsequence of nk, the row measure of the same set is equal to 0, sorry. What did I say? Yeah, the mu measure is equal to 1, okay? Now I want to prove that the row measure is equal to 0, okay? Okay, but then I will again use the Bouard-Dupuy formula. So in order to prove that this, the row measure of this term converges to 0, what I'm going to do is prove that for some, so as there is an nk missing here, I will prove that this, for the previous sequence, so the exponential of Cnk to the power minus 3/4 Rnk converges to 0 in L1 of rho, okay? Which means that what is in the exponential, extracting again a subsequence, will converge to minus infinity rho almost surely. So not to 0. So to 0 with probability, rho probability 0, okay? And so I want to prove this. So again, what you do, oh, sorry. Yeah, sorry. Ah, je vais y arriver. Okay, so what you do is that you again use the fact that you know that the rho measure is the limit of some rho m measure, okay, where you have so the rho m is the previous projected measure on the Galerkin approximation. And so the integral on the right-hand side, you can write it like, as a normalizing constant again time lambda mk, okay? We know that this lambda partition function is uniformly bounded, so we don't really have to take care of it. But the lambda mk, we will again use the Bouard-Dupuy formula, okay, to write it like the infimum on all the drifts. But this time, in addition to this, okay, I skipped something, I think. Yeah, because I did not explain how I constructed the measure, actually. So so you don't know what this Rn, so I have to explain what this Rn is here. And, okay, so in the construction, what we did is that we added this constant Cn that diverges on Rn, so we have a new Rn sharp, okay? But you don't see it as exactly as you mention it because it will cancel with the extra term in the partition function, so you don't see it. Yeah? So it's the same measure. I don't change the measure, it's just that I change the term in the exponential, okay? And then I have a uniform bond for this term, okay? Then I can use the Bouard-Dupuy formula, and that allows me to construct a measure. This is the way I did, okay? So now, going back to the proof of singularity, I use again this Rnk sharp in the Bouard-Dupuy formula, because this is the same measure. And now I have these terms. So I have the two terms I had before when I wanted to construct to prove the limit of the partition function, but I also have this extra term here, which comes from this. Okay, and we've already seen that these two last terms will compensate, so they are uniformly bounded from below. But this term is equivalent, this can be again exactly computed, this is equivalent to minus 1/2 of Cnk to the power 1/4 with the powers I've chosen before. So it goes to minus infinity. Okay, and this is the way, very simple way you prove that this set has rho measure 0 if you re-extract again a subsequence. Okay, so I have still 2 minutes. So I just want to make a brief comment on what we can do also in dimension 1. So we proved this some years ago. Dimension 1, you have everything which works well. So you have the strong Feller property, the transition semi-group is irreducible. So you got the ergodicity of the invariant measure, and you can prove the exponential mixing, that is the convergence to equilibrium. This is done by using the Poincaré inequality here, which you can prove easily by using the purely dissipative dynamical system. Okay, not the other one, but okay. But then, since this is only a property of the measure, you can apply it also to the complete system. Now, so in dimension 1, we have a rather complete overview. In dimension 2, so we saw that the Gibbs measure is singular with respect to the Gaussian measure, underlying Gaussian measure, which is different from the 542 on the torus. As I said, invariance for gamma equals 0, that is for the purely Hamiltonian system, is still an open problem, because, of course, the trouble is that you have to have a well-defined flow in this space, and up to now, to my knowledge, this is not done. This is done in very particular case, for example, if you have radial solutions and things like that, but it's not done in general. We expect to get ergodicity and convergence to equilibrium. So the information we need on the support, this is okay, but on the support of the noise, I mean, with the weak products. We need this to replace the irreducibility. We don't really have to prove the whole irreducibility. This I don't know how to do, but just prove that 0 is in the support, and this we can do. We are working on a strong failure property, but we quite believe it works, but it's not done yet. In dimension 3, there are some results about local existence by using para-control calculus that was done by Reika Fukuizumi, so my collaborator with other people in Nancy. Up to now, they don't have the global existence, and okay. There are still things to do in that direction. And I think I'm stopping here. Thank you very much.